Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be starting a three-chapter series dealing with our chapters on the atom. Chapter 6, Chapter 7, and Chapter 21, we're going to combine parts of all three chapters into one test, one set of ideas. And today we're really going to be looking at the first three sections of Chapter 6. Now, if you take a look at the ideas represented in these three chapters, 6, 7, and part of 21, what you're really looking at is, on a typical AP test, about 7 of the 75 questions be represented by these ideas. And on the FRQ section, typically every single year you're going to get a question related to some of the material that we're dealing with in these three chapters. So what we're really doing is combining all the chapters relevant to understanding the atom into one general test. And today we're just going to be looking at the first three sections of Chapter 6. Now, our discussion at the beginning here is really looking at classical physics. And classical physics typically treated particles as one type of behavior, and energy displayed a different type of behavior. Energy acted like waves, and particles behaved like particles. And classical physics treated both of those things as different things. Now, in our look at classical physics and understanding energy a little bit better, we really need to understand some of the terminology and concepts related to how we treat and describe energy. And energy is typically treated as a wave. So to really understand electrons and the electronic structure of the atom a little bit more, we're going to begin by looking at what classical physics said about energy and waves. And then we're going to translate that into what's going on with an electron. Now, in order to really understand electromagnetic radiation and other forms of energy waves, you need to understand the wave a little bit more. First off, the distance between corresponding points on adjacent waves is known as the wavelength. And if you remember from pre-AP, the symbol for wavelength is the Greek letter lambda, which looks like that, and it's pronounced lambda. So wavelength is literally the length of a wave cycle, which would be the length between two corresponding points on side-by-side waves. Technically, this is what we would call one wave cycle, and the length of that would be one wavelength. Well, since it's difficult to sometimes measure from the origin to the origin, it's easier to find tops and bottoms, which would be called crests and troughs. We typically measure the wavelength from a wave by looking at crest to crest height. And that's going to be the exact same length as one wave cycle. So what you're really seeing in this picture is two wave cycles. So wavelength would be one characteristic property of waves that you should have a fundamental understanding of. Typical lengths would be whatever length is. It would be a meter. But often we're dealing with very, very small wavelengths. So you may see things like nanometers and so forth when we're dealing with wavelengths, which we'll get into later. Now, wavelengths are usually measured in meters, as I said, or nanometers. And a nanometer is 1 times 10 to the negative 9th meters. So nanometers are very, very small amounts. So we're dealing with a billionth when we talk about a nanometer. Now, another common way to measure wavelength is the angstrom. And an angstrom deals with 10 to the negative 10th. And really where angstrom comes in is when we're dealing with visible light to get normal numbers. Sometimes it's more convenient to deal with angstroms. So it's another very, very, very small unit of length. So we're dealing metric, we got meters and nanometers, and we also have a unit of angstrom, which really represents 10 to the negative 10th. So technically it is another metric way of looking at length as well. So typically we measure wavelength in one of these three ways. Now, the amplitude is the height of the wave from the origin to the top of the crest. And amplitude really involves intensity of the light. The more intense it is, the higher the amplitude is going to be. And for all intents and purposes, really isn't something we discuss or do much with typically in AP chemistry. So that's about the only time we're really going to discuss the concept of amplitude. Now, frequency is another very important characteristic of a wave, just like wavelength is. Now, the number of waves passing a given point in a given unit of time is known as the frequency. With wavelength, we use the Greek symbol for lambda, which is that weird looking giraffe type thing. For frequency, we're using nu, which looks like a little crooked V. So don't confuse this with a V. Typically, it's written a little bit more exaggerated, and you'd see a crooked looking V like that. That stands for frequency, and it's pronounced nu. So when you take a look at the pictures we've got here, we've got two different waves. And if this is a time-lapse picture over, let's say, in 1 second, the frequency would be how many wave cycles go by in a second. So we take a look, well, there's one wave cycle, there's two wave cycles, 3, 4, and it looks like that would be about a half a wave cycle. So this would be about 3/4 of a wave cycle. So we have 1, 2, 3, 4, and 3/4 waves going by. So 4.75 waves are going by per second in that top picture. Now the bottom one, there is one wave cycle, there's two wave cycles. So if this was a time-lapse picture of 1 second, this would be 2 waves per second. So these would be, based on the picture, if this was a time-lapse picture over a second, that would represent a higher frequency, 4 3/4 waves going by in a second. Let me get rid of all of this. Now, typically, when we're talking about units of frequency, because we're counting waves per second, that gives you kind of an odd unit. Technically, that would look like this. How many per second would be s to the -1, or 1 over s. Typically, we convert that unit into hertz. So a couple seconds ago, I said this was 2 waves per second. This would really represent 2 hertz of frequency. So typically when we're dealing with frequencies, you're going to get inverse seconds or hertz, which just is a simplification of the term inverse second. And then finally, because just like with wavelengths, sometimes we're dealing with very, very, very small wavelength, because sometimes we're dealing with very large frequencies when we're looking at electromagnetic radiation, you also may see megahertz in a problem, and that really means million. So mega is million. So 1 megahertz is 1 times 10 to the 6th hertz. So nanometers, angstroms for wavelengths should be units you're familiar with. And for frequency, it's going to be hertz. And be familiar with the concept of a megahertz. Now, for waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. So if these two waves are both traveling at the speed of light, which is a characteristic property of electromagnetic radiation, you'd notice that the higher frequency one on top has a smaller wavelength compared to the larger wave at the bottom. So the relationship is the longer the wavelength, the smaller the frequency. The greater the frequency, the smaller the wavelength. So between these two waves here, you can see that visual relationship. So fundamentally, the wavelength and the frequency of a wave are inversely proportional to each other. When one gets bigger, the other gets smaller. Now, all electromagnetic radiation, which visible light is a form of, they all travel through a vacuum at the speed of light. So they travel at the same speed, which is 3.00 times 10 to the 8th meters per second, which is a constant you should remember from pre-AP chemistry. This number, do you need to memorize it? No, it's on the AP constant sheet. One word of warning, even though we don't typically use it this way in the chapter for math problems, so we get more significant digits, on the AP sheet it's given as 3.0 times 10 to the 8th meters per second, which locks us into only 2 sig figs when we're doing math. But for most of the time, we're going to be using the 3.00 times 10 to the 8th meters per second, so we get more significant digits in calculations. Now remember, visible light is only one type of electromagnetic radiation. You should remember this discussion from pre-AP chemistry. Radio waves, microwaves, infrared, all are lower in energy and frequency than visible light, and then above visible light we have ultraviolet, X-ray, and gamma ray. Those would be our higher frequency, shorter wavelength types of electromagnetic radiation. And really, electromagnetic radiation follows this full spectrum of different types of electromagnetic radiation. Every single one, the radiation is moving at the same speed, 3 times 10 to the 8th meters per second, which is flying. So the relationship between wavelength, frequency, and speed of light, you should remember pre-AP chemistry as the speed of light would equal wavelength times the frequency. So as an inverse proportionality, when one gets bigger, the other gets smaller. When you multiply, they still equal the same constant, and that constant would be the speed of light. So one type of calculation you should be prepared to handle at different times in this chapter is if you know the wavelength, you should be able to calculate the frequency, and vice versa using the speed of light equation. So, and this is also on the AB constant sheet. So it's one that you need to be able to use. Now I mentioned a second ago that radio waves, microwaves, and infrared were all lower in frequency and lower in energy than visible light. That's because there's also a proportionality relationship between energy in these things. So energy is directly proportional to the frequency. So lower frequency means lower energy for something like radio waves. So down in the radio part of the electromagnetic spectrum, that would be the lowest in energy and frequency. Up in gamma rays would be the highest in energy and frequency. And remember, wavelength, the exact opposite relationship. Now, quick math problem. What is the wavelength of a microwave having a frequency of 3.44 times 10 to the 9th hertz? So we're given frequency and we're asked to find wavelength. Remember, the relationship between them is frequency times wavelength equals the speed of light. And as a constant, we can then use the speed of light to convert one to the other. So if we want to know wavelength, we take the speed of light and divide it by the frequency. Speed of light is 3.00 times 10 to the 8th meters per second. The frequency was given as 3.44 times 10 to the 9th hertz. Now notice when I wrote it into the math problem, I converted the hertz to inverse seconds. The reason is it's easier to see that in this calculation then, the inverse seconds cancel each other in both cases, and we're going to be left with 8.72 times 10 to the negative second meters. So whenever you see hertz, recognize it's actually 1 over s. Whenever you see 1 over s, recognize it's hertz. And you need to be able to convert back and forth between the two. So this is a type of calculation you should be prepared to do in a number of different situations throughout the chapter. If you ever know frequency, you can get to wavelength, and vice versa using the speed of light equation. Another typical problem. Let's say we have a helium neon laser that emits light with a wavelength of 633 nanometers. I mentioned you should be familiar with nanometer, angstroms, and megahertz. Here's an example of seeing nanometers in a problem. Now, if our speed of light equation is the speed of light equals frequency times wavelength, and if they're giving us our wavelength, we should now isolate frequency, and frequency would be the speed of light divided by the wavelength. Now the problem is 633 nanometers is not in the same unit the speed of light is. Remember, speed of light was given in meters per second. So before we can plug into this equation, we first need to convert nanometers into meters so that we can make a common calculation here. So we've got a speed of light, which is meters per second. We've got wavelength, which is nanometers. But right now, as is, these things don't convert. And remember, 1 nanometer is 10 to the negative 9th meters. Now, you can look at this with fancy dimensional analysis if you want. We don't want nanometers. We want meters. Nanometers would cancel, and we would end up with 6.33 times 10 to the negative 7th meters. Now, before I move on, I want to make a brief mention of another way to do this. If you want to save time and do this the quick way, remember, nano means 10 to the negative 9th. So on the bottom here, if we just take 633 and put times 10 to the negative 9th, I know that's a non-standard notation, and it's not a proper way to display a number for an answer, but there's no reason to use, we can't use this in the middle of a problem. So rather than going through all this garbage, the easy way to do this is instead of using 6.33 times 10 to the negative 7th, just use 633 times 10 to the negative 9th meters, and it works perfectly fine. So just do a simple substitution, and it will make the math here significantly easier. So don't go through the extra step and convert. Just write it 633 times 10 to the negative 9th if you want to take the shortcut here. Now at this point, now our units will cancel, and we're going to be left with inverse seconds. But remember, we typically write that with units of hertz. So you'd typically see this answer expressed as 4.74 times 10 to the 14th hertz. Now, the next section gets into a problem with classical physics and classical understanding and treating particles like atoms and electrons and so forth as particle nature and adhering to particle physics, and energy forms like electromagnetic radiation adhering to the wave equations and relationships. Well, the problem is there was a number of phenomena that really scientists couldn't explain using the wave model of light. Light is an energy form. By classical physics, light is supposed to behave like it's a wave. But things like black body radiation, which is really the emission of a glowing metal, so when you heat up a metal, it kicks out light, The photoelectric effect, which was something that Einstein was studying, which we'll look at, as well as emission spectrum. These three fundamental things, which we could observe at this point in time, we really couldn't explain by classical physics. So in each of these situations, light really wasn't behaving as if it was a wave. And that was very, very, very foreign to scientists. Light as an energy form was supposed to be a wave, and it was supposed to be able to be explained by wave properties. And honestly, these are three examples of how we couldn't explain light if we treated it like a wave. And what we ended up doing was treating light like a particle. And this went against classical physics. Now, the first person that we're going to look at here that did this was a man named Planck. So the wave nature of light really couldn't explain how an object can glow when its temperature increases. And this is known as black body radiation. Max Planck explained it by assuming that energy comes in little packets or bundles called a quantum of light. Now what he was doing was treating light, which is an energy form and is supposed to behave like a wave, as if it was a particle. So he's looking at particles of light here. So a quantum is really a particle of light, which he ended up calling photons. So a photon is basically a particle of light. And Max Planck really thought outside of the box in trying to explain black body radiation. What he said was, well, traditional wave mechanics don't work, so why don't we treat this energy form as if it's a particle and see if that can explain its behavior. So a quantum is the smallest amount of energy that can be emitted or absorbed as electromagnetic radiation. It's this little bundle of light energy. Now Planck found that the energy of a quantum of light is directly proportional to the frequency by this equation. So what he was doing here was coming up with a mathematical relationship relating the frequency of a electromagnetic radiation as if it was a bundle of light energy called a photon. And he could calculate the energy of that bundle of light using this equation. Now the H is Planck's constant, and the crooked looking V is nu, that would be frequency. So Planck's constant is 6.626 times 10 to the negative 34th, a number you don't have to memorize because it is on the AP constant sheet. But you should be able to do these calculations. If you know the frequency of a bundle of light, you should be able to calculate the energy of that photon using this equation. So what this would look like is a math problem. What's the energy of a photon from the violet portion of the rainbow if it has a frequency of 7.23 times 10 to the 14th hertz? So we have one photon, one little light particle, one little bundle of violet radiation at this frequency. What would the energy of that photon be? So remember, what we're really looking at is the energy of a particle of violet light. So if you use this equation and plug in, Planck's constant is 6.626 times 10 to the negative 36 joule seconds. And while it looks like hertz needs to be converted into something else, remember hertz is really an inverse second. So when we multiply these two, seconds will cancel and we'll be left with units of energy, the joule. So this has to be a proper calculation. We didn't have to do any extra steps here. Remember, if you're given megahertz in a problem, you would have to convert that to hertz. Remember, mega means 10 to the 6th, so you can do just like I did before. If it was 723 megahertz, that would be 723 times 10 to the 6th hertz. You can do that same substitution if you need to. And as far as our calculation goes here to 3 significant digits, the energy of this photon of light would be 4.79 times 10 to the negative 19th joules. Why is it such a small energy amount? Remember, we're talking about one bundle of light energy, one photon. If we had a mole of photons, we'd multiply this times Avogadro's number, and then for a large number of bundles of light energy, we get a significantly greater amount of energy. So remember, the reason it's so small is we're looking at one photon of light energy here in the violet part of the spectrum. Now, combining the two equations we've talked about, the speed of light equation and Planck's equation, you see that they both share something in common. They share frequency. So we can solve for frequency in one and substitute into the other, and we can derive a relationship that looks at the relationship between wavelength and energy. Now remember earlier I said wavelength is inversely proportional to frequency. Here you can see that wavelength is also inversely proportional to the energy. And remember HC, that's multiplying two constants together. So that's really just a greater constant. So if we're given the wavelength, we can calculate energy without having to use both equations. So all we've really done here is combine those two equations into one equation to simplify the math a little bit. If we knew energy of a bundle of light, we could calculate its wavelength. If we knew the wavelength of a bundle of light, we could calculate its energy. But remember, we need to use the two constants here, both Planck's constant and the speed of light constant. And what really he was doing was treating light, which is supposed to be a wave, as if it was a particle. Now, once Planck had come up with his black body radiation explanation, other scientists started to realize, well, maybe there are other instances where we can also explain things by looking at light as if it's a particle. And Einstein did this with the photoelectric effect. So he used these same fundamental assumptions that Planck was using, that sometimes light can behave as it's a particle, to explain something that scientists couldn't explain, which is called the photoelectric effect. If you have a solar calculator, your solar calculator gets its energy through an application of the photoelectric effect. There's a little photovoltaic cell. When light with enough energy and frequency hits it, it'll cause electrons to move, and a movement of electrons is electricity. If light with too little energy or frequency hits, nothing happens, and it doesn't work at all. So if you took red cellophane and covered the photovoltaic cell on your graphic or on your solar calculator, the calculator would cease to work after a few minutes once the energy that was stored in it died down, because literally you're not getting enough energy to make electrons move. Well, scientists couldn't explain with traditional physics how that would happen. And really what Einstein did was apply the same ideas that Planck was using. Einstein assumed that light traveled in energy packets called photons. And the energy of one photon was established by Planck, E equals h nu. Light shining on the surface of metal can cause electrons to be ejected from the metal, but only if the light was coming in as a large enough particle. So if the particle was too small, it wouldn't make electrons move. If the particle of light coming in was big enough, it would make electrons move, and electrons will get ejected from the piece of metal. What we're really doing is treating light, once again, as if it's a particle. So the electrons would only be ejected if the photons had sufficient energy or sufficient frequency. Below that threshold frequency energy, no electrons would be ejected. Above the threshold frequency, an electron would be ejected, and what would happen is the excess energy appears as kinetic energy of the ejected electron. So the ejected electron would carry more kinetic energy if you were above that minimum threshold. So just being above the threshold, you're still kicking out one electron per photon. It's just that the electron emitted is going to come out at a higher kinetic energy value. Now, another application of treating light as if it was a particle was really in understanding what's known as the bright line spectrum, or the line spectrum. And this is really the beginnings of Bohr coming to have a better clue as to what was happening with electrons inside an atom. So our understanding of the bright line spectrum is critical to really our understanding of where the electrons are at, and critical to how Bohr was able to come up with some of the things that he discovered. Now, another mystery in the early 20th century then was the emission spectrum, which is basically when you pass light, or I should say you pass electricity or energy through an atom or a molecule, and the atom or molecule starts to glow. And what comes out is not one particular frequency of light, but a whole bunch of different frequencies of light. And this isn't like white light where you get all of the colors of the spectrum. You really get what's called a discontinuous spectrum. So before we get into the bright line spectrum, we need to look a little bit at some of the words I'm going to be using at times. Now, if you have light of only one wavelength or frequency, it's known as monochromatic light, one color light. One specific frequency of violet is what we looked at in calculating the energy of our violet photon before. So that would have been an example of calculating the energy of monochromatic light in the violet part of the spectrum. Now, radiation that spans a whole array of different wavelengths is known as a continuous wavelength. White light, if you split white light into its component colors by passing it through a prism, you would see it gives you the continuous spectrum. You get all of the colors of Roy G. Biv. That's known as a continuous spectrum. Light of one specific frequency on this continuous spectrum is known as monochromatic light. So when radiation from a light source such as a light bulb is separated into different wavelengths, you get a continuous spectrum. You get all the different colors of the rainbow. Now that's white light, what comes out of the sun and what comes out of glowing metals and light bulbs. But when you take a look at the light that comes out of an atom, while it's got multiple colors in it, it's not the full continuous spectrum. So what you observe is what's known as a bright line spectrum. You get only a few of the colors of light coming out. So only some of the different colors that might be visible are going to be visible, and that's why we call it a bright line spectrum. You see a few bright lines instead of all of the colors of the Roy G. Biv. So this is a continuous spectrum, and this is a, down here, this is a discontinuous spectrum. Of the whole purple all the way down to red, we only see a few different colors with sodium, and with something like hydrogen, there are a few more colors you can see at these different spots here. And when you actually see the glowing light coming off of the substance, really you see a mix of the different types of monochromatic light that are coming out. But what you get with a glowing atom or molecule is not the continuous spectrum, but a bright line spectrum. Scientists couldn't explain using particle, or I should say, using wave theory, why you get a discontinuous spectrum with glowing substances. Now, the first person who really was able to put together what might be happening and have a greater understanding of the bright line spectrum was a scientist by the name of Bohr. And he used this as his basis for understanding the electron that is inside a hydrogen atom. So Bohr noted that the line spectrum of certain elements, and he used that to try and assume what was happening with the electrons and the energies that those electrons existed at. And he called this orbital. Now, when you orbits, when you think of our modern view of the atom, if you go back to pre-AP chemistry, remember we talked about the place where electrons lived as orbitals? Well, an orbit is not the same thing as an orbital, but orbital really comes from this Bohr theory of what was happening with the electrons inside atoms as living at specific orbits around the nucleus. It's a little too simplistic, so there's some problems with the Bohr model, but this is what got the ball rolling. So this was critical for our next stage in understanding of the electrons inside the atom. So hopefully you'll be watching this movie. Otherwise I'll have to move the movie to
If a sample of hydrogen gas is heated, it gives off light. When you view this light through a prism, you'll see an emission spectrum consisting of bright lines at specific frequencies. Because the spectral lines come at definite intervals, this suggests that specific energy levels exist in the atom. A cross-section of an atom shows the energy levels similar to the rungs of a ladder. When energized, the electrons move temporarily to higher energy levels. As the electrons fall back to lower energy levels, they lose energy in the form of light, which produces the characteristic spectrum of the element. Because we know that the emission spectrum for each element is different, we also know that the distances between energy levels must be different for every element.
a link on school notes and you can watch it there. So hopefully I'll be able to splice and include it in this movie when all said and done. Now, what Bohr was looking at then was an understanding of where the electrons were at inside the atom in terms of a location as well as an energy. And the reason he came up with his ideas about electrons existing on these orbits was because of what we knew about the bright line spectrum. And he knew that when you had an atom, and you had a simple atom like something like hydrogen, so we only had one electron, the electron could only exist at certain specific energy amounts inside the atom. And when the atom would absorb energy, it would jump up to a higher energy amount. But once again, it was still a very specific energy that existed at. The electrons can only exist at these certain specific energies he called orbits. Now, it's unstable when it jumps up to higher energy. The lower potential energy you get, the more stable you are. So when an electron jumps up to a higher energy orbit, it's unstable, so eventually it's going to fall back down. And when it jumped up, it was absorbing energy, so when it falls, it's going to release energy. And he was basically studying bright line spectra of atoms to try and look at where the electrons were at and what these energy orbits were, and of devising an equation that worked great for hydrogen. So Niels Bohr adopted Planck's assumption and basically explained what was happening with the bright line spectrum and what was happening with electrons inside atoms by looking at these fundamental assumptions. He said only orbits of specific radii, so we're talking about a specific distance from the nucleus, and corresponding energies. So basically he said energy and electrons inside atoms existed at specific distances and specific energies inside atoms. In other words, they were quantized. Electrons didn't exist at any energies, they only existed at certain specific energies. So there are only some very specific energy amounts that these electrons can be permitted to exist at inside an atom. 2, he said electron in a permitted orbit has a specific energy and it's an allowed energy state. So it exists at specific energies and specific energy states inside an atom. And energy is only emitted or absorbed by an electron as it moves from one allowed energy state to another. So if you had an electron that was at its first energy state, it would absorb a very specific amount of energy when it went to the second energy state. And therefore, it would absorb that energy, and when it fell, it would then release that exact same amount of energy, and the light that came out would be at a very specific frequency and energy. And if it's in the visible spectrum, it would be at a very specific color. So if you went from the first to the second, it would absolve that type of absorption of energy. If it went from the second to the third, it would absorb another quantum or specific amount of energy. So basically, electrons only exist at certain specific energies, and as they absorb and release energy, it's gaining and losing energy in very specific bundles. Now, the energy absorbed or permitted from the process of an electron promotion or demotion can be calculated by this equation. And this equation, by the way, is on your AP constant sheet. So the energy in the hydrogen atom, because that's what we're really looking at here, is the energy in our hydrogen atom at different energy amounts. N would represent the energy state that we're talking about, or principal quantum number, which is what we'll eventually call this. So at energy level 1, you could plug in a 1 here and you could calculate what our energy is. Now, everything on top here, the Hc and Rh, which is known as a Rydberg constant, all of those are constants, so we can combine them together into one large constant that looks like this to simplify the equation. So on the AP constant sheet, if you know what the energy level is, you can calculate what energy level you're on, 1, 2, 3, 4, 5, 6, 7, and so on. You can calculate the specific energy of that energy state. So if you knew you were going from energy level 2 to energy level 3, you would calculate your energy with a 2 right here. Then you would calculate your energy with a 3 for N, and take the difference in those two energies, and you would see how much energy was absorbed or released when an electron jumped from the second to third. That would be absorption of energy, or fell from the third down to the second. So for the hydrogen atom, you can very accurately predict what types of energy you're going to get for different jumps and drops from different energy levels within the atom. Now, the problem with the Bohr model was this worked beautiful when we had one electron in a hydrogen atom. We could very, very accurately calculate not only what we can see in the visible spectrum, but also what we can see in the infrared and ultraviolet spectrums, things that scientists didn't even know existed at one time. We could also predict what energies would be in those parts of the non-visible spectrum using Bohr's equation. The problem was when you got to 2 electrons, the math just didn't work as well. And when you get to 3 electrons, it worked even worse. So his model worked great for 1 electron and totally fell apart after that, which told scientists that he was onto something, but his ideas were incomplete. There must be more to it than that. So really, the Bohr model could not explain the spectrum of any atom other than hydrogen, but mathematically it beautifully predicted hydrogen. And we also now know the electrons really don't move about the nucleus in these circular orbits that he called these orbits that they were based upon inside the atom. So part of his model was fundamentally flawed, but at least it got us thinking in the right direction that electrons can exist at certain specific energies and only at certain energies. It must just have been a little bit more complicated than his fundamental idea was. So his model did really introduce 2 very crucial ideas. First, the energy of electron is quantized. Electrons can exist only in certain energy levels, and we describe those energy levels using quantum numbers, which is something we'll get into tomorrow. And energy can be gained or lost as electrons move from lower to higher energy. That's an absorption of energy, or loss when they fall from a higher